The Electron-Ion Collider, EIC, offers a unique opportunity to explore new physics beyond the Standard Model, SM, through its high center of mass energy and coherent interactions of large nuclei. This research focuses on the discovery potential of light-weakly interacting vector bosons from various models via clean displaced vertex signals at the EIC. The motivation stems from the need for new physics beyond the SM, which can be explored by searching for low-mass particles with feeble interactions. The EIC has a competitive advantage in this search due to its high center of mass energy and coherent interactions, leading to enhanced interaction rates. 3 representative models of light-hidden vector bosons are considered, characterized by mass scales of 100 MeV, and produced by coupling to the electron beam. These models include a standard dark photon, a gauge boson coupled to the BL symmetry of the SM, and leptophilic gauge bosons that couple to lepton flavor number. The EIC's high beam energies, combined with its expected integrated luminosity, provide a significant reach in searches for new physics. The process under consideration is ultraperipheral production of a massive light vector boson A, represented by the process EAZ right-pointing arrow EAZA. If A is light enough, its decay will be displaced relative to the production vertex, yielding a signal with virtually zero SM background. The importance of far backward particle identification capabilities in the EIC detector complex is highlighted, as it can improve the reach for new physics. This study builds upon previous studies on phenomenology of axion-like particles at the EIC and similar searches for displaced hidden vectors at the Muonnet experiment. Overall, this research demonstrates the potential of the EIC to discover or constrain light-weakly interacting vector bosons over significant parts of their parameter space, favorably comparing with or surpassing existing experimental projections for the models examined. At the Electron-Ion Collider, EIC, a hypothetical dark vector boson, A, can be produced through the collision of an electron and a gold ion, resulting in the emission of the A from the electron, which subsequently decays into an electron-positron pair. The authors investigate 2 detection scenarios, one within the current EIC tracking capabilities and another with a proposed far-backward detector. The amplitude calculation and cross-section integration for this process involve phase space restrictions due to the EIC's electron detection capabilities. The probability of a displaced decay that is detectable depends on the A lifetime, its boost, and speed in the lab frame. Signal selection criteria involve identifying an electron and a positron each displaced from the primary vertex. The corresponding cross-section for signal events is given by equation 4, which includes the probability of displacement, the differential cross-section, and the branching fraction into electron-positron pairs. Numerical integration over the pseudo-rapidity and boost of the A yields the base EIC limits and the far-backward detector scenario limits. The vector boson electron coupling, GA, influences the lifetime tau in the displacement probability, PDISP, which appears on the right-hand side of equation 4. By calculating the cross-section for signal events, the authors establish a foundation for determining the discovery potential of the EIC for the hypothetical A dark vector boson. The proposed far-backward detector scenario offers enhanced sensitivity to the A signal, highlighting the potential for future upgrades to the EIC detector. The authors delve into the potential backgrounds and limitations of their study on dark photons in electron-ion collisions, assuming a negligible standard model background due to large displacements and sparse detector regions. To eliminate photon conversions, they suggest removing displaced vertices originating from silicon tracker disks. Reconstruction of the invariant mass of lepton pairs could also differentiate A events from photon conversions. Misidentification of charged pions as electrons or positrons is considered negligible due to the low fake rate in the electron endcap. Signal reduction caused by electrons or positrons lost down the beam pipe is estimated at 2030%, but not included in projections. To establish limits on the coupling GA, the authors utilize equation 5, which depends on the upper limit of the 95% confidence interval on the mean number of signal events given 0 expected background events. They take the luminosity to be 100 fb1, A, consistent with Ref. 2. The dark photon, a vector boson of a hidden U(1) gauge symmetry, has garnered interest as a link between a new sector containing dark matter and the Standard Model. A kinetic mixing term between the U(1) and the Standard Model hypercharge field strength tensors is introduced, denoted by equation 6. In Fig. 2, the authors present their projected limits for displaced dark photons from the EIC, compared to various existing limits and projected limits from current and future experiments. The solid-filled region represents their baseline projection using the epoch detector and a luminosity for gold-ion collisions of L equals 100 Fb(1) A. Projected constraints on the interaction strength of U(1) vector gauge bosons are discussed, with a focus on the B-L and leptophilic gauge bosons. The B-L gauge boson, in particular, is subject to stringent constraints from the Electron-Ion Collider, EIC, as shown in Figure 3. These constraints are further augmented by additional projections from Bell E, Dune, and a recast phasor projection. Notably, the EIC provides a significant reach in the parameter space, especially when a far-backward detector is included, allowing for a more comprehensive exploration of the B-L gauge boson's properties. In the context of leptophilic gauge bosons, differences in lepton flavor numbers are crucial, necessitating small coupling constants to ensure consistency with experimental data. Interestingly, searches for displaced bosons at the EIC are also sensitive to these particles, providing an alternative avenue for their detection. This highlights the EIC's versatility in probing the properties of U(1) vector gauge bosons, including both B-L and leptophilic gauge bosons. By exploring these gauge bosons, researchers can gain valuable insights into the fundamental forces of nature and the structure of matter itself. The authors establish projected limits on leptophilic gauge bosons that couple to electrons, analogous to those obtained for the Bl gauge boson scenario. Figures 4 and 5 illustrate these limits, showcasing distinct sensitivity to specific regions of the parameter space, particularly with a far-backward detector. The future Electron-Ion Collider, EIC, is poised to probe light-hidden vector bosons with masses ranging from a few to hundreds of MeV and couplings much weaker than 1 to the Standard Model fields. The EIC's capabilities surpass those of other collider experiments due to the nuclear charge Z enhancement of the cross-section. In a clean, background-free regime, the authors focus on parameters where produced vector bosons have sufficiently long lifetimes, resulting in displaced decay vertices in the detector. With realistic integrated luminosity allocations of approximately 100 Fb(1) A, coupling parameters as low as 5 by 106 can be probed. The addition of far-backward particle detection capabilities at the EIC can extend the reach to couplings of approximately 106 and masses up to Ma of approximately 500 MeV. The analysis assumes excellent electron final state identification capabilities of the future EIC detector. However, significant branching fractions into mu plus mu are present in parts of the model parameter space, particularly at heavier A masses. Muon detection capability at the EIC could provide additional statistics and strengthen the bounds. Furthermore, the EIC's capability to collide polarized electrons with ions could offer an additional handle to probe the chiral structure of the A couplings. The research paper discusses a novel approach to data analysis, introducing a new methodology for optimizing data processing times. This methodology leverages advanced algorithms and mathematical formulations to significantly reduce processing times, making it more efficient for large datasets. The approach is based on the concept of parallel processing, where multiple data streams are processed simultaneously, taking advantage of multi-core processors. The authors demonstrate the effectiveness of this method through detailed case studies and comparative analyses with traditional methods, showcasing a substantial reduction in processing times. In relativistic collisions, the ion frame production cross-section is a crucial concept, closely tied to the lab frame. The energy of the initial state electron, EK, and the vector boson, cos theta k, play a significant role in the lab frame. The expected kinematics involve a boost in velocity of the ion frame, which is essential for understanding the transformation from the lab frame to the ion frame. This transformation is facilitated by the Jacobian determinant, a critical component for calculating the differential cross-section. A key aspect of this research is the decay width of a hidden vector A, which is influenced by various contributions. These include neutrinos, charged fermions, and hadrons, with the latter being particularly important. The ratio, a measure of the hadronic contributions, is a crucial factor in this calculation. By examining the decay width and its constituent parts, researchers can gain valuable insights into the properties of hidden vector A and its role in relativistic collisions. The precise calculation of the ion frame production cross-section and the decay width of hidden vector A has significant implications for our understanding of high-energy particle interactions. By exploring these complex phenomena, researchers can refine their models and make more accurate predictions about the behavior of subatomic particles. The transverse dCA is defined as the minimal distance between the particle's reconstructed trajectory and the primary vertex, projected onto the transverse plane. This distance is estimated based on the kinematic properties of the dark boson, assuming the leptons follow a straight-line path backward from their production point. The assumption of a straight-line path is justified due to the strong magnetic field in the EIC, which ensures the electron decay product's trajectories are significantly larger than the minimum dCA requirement. The relationship between the dCA and the transverse dCA depends on the polar angle phi, with the calculation simplified for the average transverse dCA. The relationship between the angle theta LL and the boost gamma is established through formomentum conservation, yielding equations B7 and B8. These equations relate the masses and velocities of particles A and L. By solving for sin theta LL, the authors derive equation B9, which approximates to 2V gamma under the condition ML equals mu much less than ma, applicable to this study. The minimum resolvable value of transverse dCA, or distance of closest approach, for particles at the Electron-Ion Collider is approximately 100 micrometers, as referenced in 15. This value is used to determine the minimum distance the dark photon can travel before being considered displaced, denoted as dmin. Equation B10 expresses dmin as a function of gamma, v, and cos theta lab, where theta lab is the laboratory frame angle. These derivations and calculations are crucial in establishing the theoretical framework for analyzing the dark photon's behavior and its potential detection at the EIC. By approximating sin theta LL as 2V gamma, the authors provide a foundation for understanding the dark photon's kinematics and its potential to be detected at the Electron-Ion Collider.